give this presentation. It's a privilege to do so, and it's an exciting time for me. I'm dialing in this morning from Oxford. It's still dark here, but it's as beautiful as ever. And I'm going to be representing a team made up of my group at Oxford and also my group in Ireland. It was a joint effort between two parts of our group. So the subject of today's discussion is the mechanism of CuO2, copper oxide high temperature superconductivity. Oops, excuse me, I need to change something. Okay, so, everyone in this audience perfectly well aware that superconductivity is profoundly useful and important state of matter. And it plays a giant role in science today. All kinds of advanced medical, bio, astrophysical, high energy physics, high field, high fusion, and quantum computing. So we need more superconductivity, and we need higher temperature superconductivity, and we need to have the material science necessary to design the room temperature superconductors of the future. That's really what we've been struggling with for a number of decades now. So I'll remind you that electrons can't really condense into a macroscopic quantum state unless they pair. And if they pair, you can write a two-particle wave function of this type. It's quite generic. It's got a real space component and it's got a spin component. And in this talk, we're just going to deal with spin singlets. So I showed the singlet component there on the top left. And you can expand this into creation and annihilation operators if you like that kind of stuff. It's shown on the top right. So even a single pair is written as a sum over the average, or the sum over two operators of opposite spin and opposite momentum. Now, if for some reason all those pairs can condense and form a macroscopic quantum state, then you have a superconductor. And I'm deliberately not saying here, Bardeen, Cooper, Schrieffer, I'm saying just if there's any mechanism, probably color superconductivity, doesn't use Bardeen, Cooper, Schrieffer. It uses other mechanisms. Probably neutron star, superconductivity doesn't use Bardeen, Cooper, Schrieffer. So the point I'm trying to make is that if you can condense a macroscopic quantum number of Fermi pairs, you get a macroscopic quantum state. It's got a macroscopic wave function with an amplitude, often called in superconductivity world the energy gap, but it's really the amplitude of the wave function, and a quantum phase. And something we'll have to keep in mind for this talk is that the modulus squared of the amplitude is the number of condensed particles in the condensate, the number density of pairs. Now, here's Bardeen, Cooper, Schrieffer. In this gloriously beautiful theory, you consider fermions of opposite momentum and opposite spin, and they interact in a two-particle fashion through an interaction potential of VKK prime. Of course, that's true in general for any gas of fermions, but we just focus on this scattering process. BC and S hypothesized that the many-body wave function is the one shown there on the right, capital Psi. It's a product state. It's not entangled, no matter what your high-energy colleagues tell you. It's not an entangled state. It's a product state. But it's a product state of singlet pairs. With that product state, you can write down the BCS theory. So you write the order parameter, delta K, as the sum over momentum space for the interaction potential, VKK prime, that's a Fourier transform of the interaction potential in real space, times the average value of this anomalous operator, C minus annihilation minus K spin down, annihilation plus K spin up. Now, you'll be stuck unless you had a wave function which you could calculate the value of that average. But we have the BCS wave function, so we can calculate that average of C And it's this famous gap function. There's a self-consistent function. If here, for a given interaction potential V and for a given band structure E of K, a solution for delta of K can be found, then we say we have a BCS superconductor. Its energy gap, its order parameter is 1.76 times kBTC for S wave. That's has guided our thinking now for half a century, and it's a magnificent piece of theoretical physics. But it's not the general case. The general case is any mechanism which will condense an anomalous average, C up, C down, averaged over the whole wave function, not equal to 0. And that mechanism does not have to be BCS. All right. Now let's turn to CO2. You all know, starting in the 80s, some of you even remember, a few of us remember, when the cuprates were discovered, TC started shooting up. In fact, 35 years later, these are still the highest critical temperature ambient superconductors. They still represent the best starting point for room temperature superconductive electronic technology that we have available now. Now, admittedly, the hydrogen sulfides and lanthanides appear to superconduct at room temperature, but only at hundreds of millions of atmospheres. At ambient pressure, the cuprates are still our best superconductors. And we'd like to actually control them by understanding what pairs the electrons together in these compounds at such tight, strong binding energies and superconduct at such high temperatures, minus 100 degrees centigrade. Now let's think of the electronic structure. So the CO2 plane is a square lattice of copper, oxygen, copper. The coppers are in the 3D9 state. To put them in the 3D10 state requires a Coulomb energy, U, which is about 3 electron volts. The overlap integral of copper and oxygen makes what would be a hopping rate of around 400 millivolts. It's a very strong overlap integral. And now if you represent that as a band structure shown on the right, the 3D9 band is at the bottom, the D band. It's separated from the empty upper D band by the Hubbard or Coulomb energy U, and that's a very big energy. But when Mother Nature was inventing this material, she put the oxygen p orbitals in between. So the energy level of the 2p6 oxygen p orbitals is much higher, and the energy splitting between the 2p6 orbital and the 3d10 orbital is called the charge transfer energy. I call it epsilon. We had to change it from delta to epsilon for the experts because it's too confusing when you're measuring the order parameter of the superconductor and you call it delta, and you're measuring the charge transfer energy and you call it delta. The referees get confused. So we call the charge transfer energy epsilon. Now at half filling, Coulomb, this is a Mott insulator. It's an antiferromagnetic Mott insulator. But you can hole dope it. And hole doping, it's not like hole doping a semiconductor. What you're doing is removing an electron from an oxygen atom in the p band. And when you do that, transport begins. Some kind of a quantum mechanical state, which in my opinion is not fully understood, is created. But it allows transport through the crystal as soon as it appears. And we get this glorious phase diagram. So P is the number of hole densities per CO2 unit cell. Temperature on the left-hand axis. You only have to put 1 or 2% of holes into this compound to destroy the antiferromagnetism. A mysterious phase, which I call electronic dark matter, but other people call the pseudo gap, appears. And then by the time you get to 15 or 20% hole density, you get high temperature superconductivity. It's beautiful, but we don't know why. What is the actual mechanism that's producing this robust high temperature superconductivity in dozens of different compounds? It's quite a universal phenomenon. All right, now let's turn our attention to superexchange. And here I'm not talking about a crystal, I'm just talking about 3 atoms, 2 copper atoms in the 3d9 state and 1 oxygen atom bridging them in the 2p6 state. You can write the Hamiltonian for those 4 electrons. And, if you know what you're doing, you could diagonalize it, but, it's relatively easy to solve in perturbation theory. So you write the energy of the D states, you write the energy of the p states, you write the PD hopping rate, and then you destroy a p and create a d, or vice versa. And you write the Hubbard energy on the two copper sites, Hubbard energy U. So that simple Hamiltonian you can study. In fact, of course, it was studied in the 1950s. It's well understood for 3 atoms. But it represents very subtle physics. I'd like you to think about that. So consider the 4 electrons. The top 2 lines here are the 4 trivial conformations of those electrons. So one copper is spin down, the other copper spin up. The 2p6 orbital, each of the 2p6 orbitals is in the singlet state. And there's 2 ways of doing that in my cartoon, no problem. Now, if you have hopping from oxygen to copper, that's how the transport starts, hopping of an electron from oxygen to copper. So the middle row shows what happens. If an electron hops onto the copper site, the energy level for the 3d9 state disappears. It no longer exists in the Hilbert space, and the 3d10 state appears at a high energy. And there's 4 simple ways for that hopping to occur. And then on the lowest row is the next most interesting process, which is 2 hops, one from copper to oxygen, one from oxygen to copper. It also has multiple conformations, and so on and so on. You can solve this problem, at least in perturbation theory, and if you just focus on the spin-spin interaction, neglect the transport, then that part of the Hilbert space is described by Heisenberg Hamiltonian, and this has been known since the late 1950s, by Heisenberg Hamiltonian, SI.Sj, where Si is the spin on one copper, Sj is the spin on the other copper. And the strength of that antiferromagnetic spin-spin interaction is given by J, superexchange J, which is written there for just 3 orbitals. In the case that the Coulomb energy, the Hubbard energy, is much bigger than the charge transfer energy, and there's many transition metal materials where that's not true. Transition metal oxides where that's not true, but for the cuprates it is true. U is much bigger than epsilon. In that case, the superexchange energy is, in perturbation theory, is 4 times the PD hopping rate to the power of 4 divided by the charge transfer energy cubed. That tells the strength of superexchange between adjacent spin-a-half electrons on the copper sites. Now let's take that picture and generalize it to a lattice. Now we won't take just 3 atoms, we'll take, 10 to the 30 atoms. We'll take an enormous square lattice of CuO2. So under those circumstances, you'd have a Heisenberg Hamiltonian on the square lattice, and you can solve that in 2 sublattice mean field theory on the back of an envelope. And you all know the solution. It's an antiferromagnet. This antiferromagnet has to have the band structure of CuO2. So it has to have a lower Hubbard band, 3d9, upper Hubbard band, 3d10. It has to have the 2p6 band in between and the charge transfer separation epsilon. But otherwise, the spin-a-half electrons should form, in theory, a spin-a-half square lattice antiferromagnetic insulator, if superexchange theory is correct. And of course, that's exactly the state which occurs in the parent state of the cuprates. So what this tells us is that the superexchange picture is correct for the undoped compound. All right, now look at your CuO2 up here. There's 4 electrons, 2 on the copper sides and 2 on one oxygen side. If we take away just 1 electron, now we're in the whole doped situation. And this is a completely different, Hilbert space and really very different physics. As I just said, you get a completely new phase diagram containing unidentified phases, containing exotic density waves, containing high temperature superconductivity, all just because you took away 1 electron from the oxygen atoms. Now, high TC superconductivity. The band structure can't be changed much by, adding 5%, 10% of holes. It'll be approximately the same, but maybe a new hole-doped band, sometimes called the Zhang-Rice band, would appear at the top of the oxygen band. And we know it's a superconductor. So Phil Anderson, God rest his soul, in 1987 proposed that what happens is that you destroy the long-range antiferromagnetism, but you keep the superexchange interaction. The superexchange interaction now forms singlet pairs, and they condense to make a high temperature superconductor. So my code for this hypothesis is up here on the right. He basically said charge transfer superexchange, epsilon, is what causes the condensate of electron pairs. There's no electron-phonon interaction. There's no antiferromagnetic spin, weakly interacting antiferromagnetic spectrum of antiferromagnetic spin fluctuations. It's just superexchange which does this. That's a hypothesis, but a work of great genius, of course. Now, for those of you who remember those days, cast your mind back to the late 1980s. The world's leading condensed matter theorists were all working on, the mechanism of high TC. So look down here. So Ruckenstein, Peter Hirschfeld, superexchange mechanism. Gabby Cotliar and Liu, superexchange mechanism. Okay. Charge transfer antiferromagnetism and superexchange pairing correlations. Doug Scalapino. So this was the central idea that was being pursued in the first few years of this field. And wonderful, that's fabulous. Now, fast forward 35 years and ask yourself, what's going on in the theory of this field? It's the same. People pursuing the doped three-band Hubbard model in search of the superexchange mechanism, charge transfer superexchange mechanism of high temperature superconductivity. Of course, nowadays, the theoretical tools are immensely more powerful than they were 35 years ago. But the focus of the research remains the same, to understand whether charge transfer superexchange is the mechanism of high temperature superconductivity. And why is this focus still going on? It's because experimentally, this is an unresolved question. All right. Now let's think about the three-band Emery model. This is Vic Emery, God rest his soul. He passed away as a relatively young man. In '87, he said the correct model we should use for the cuprates is to keep the two oxygen orbitals in the band structure. So his Hamiltonian had both the energies of the states, of the 3d9 state of the coppers and the energies of the 2p6 state. So alpha and beta sum over both copper and oxygen orbitals. He kept the Hubbard energy on the copper side. It was known to be there. And he kept all possible hopping processes between different orbitals. That Hamiltonian was not solvable in 1987, and that Hamiltonian is not solvable in 2022 in an analytic form. But we have modern theory tools, and I'm not a theorist, but I just want to sketch for you dynamical mean field theory. So suppose you have a complicated correlated problem you want to solve, like the three-band Hamiltonian for the cuprates, shown in the white box in the middle. So in DMFT, what you do is embed a small, let's say 3 atoms or 12 atoms, or a small number of atoms, a cluster of the atoms with their correct Hamiltonian, embed that in an effective medium, which is a metal, Green's function for delocalized fermions. Then you solve for the impurity states, which are created by your accurate Hamiltonian cluster embedded in the medium. If you find that solution, you extract the self-energies. Using the self-energies, you update the Green's function of the medium. And then you check, does the Green's function of the medium, is it consistent with the Green's function of the CO2 model you're trying to solve? And, typically it's not on the first iteration. So you go around again, you update the Green's function of the medium with the new self-energy, and now you resolve the impurity problem. And you just go around and around and around until the Green's functions of the effective medium are indistinguishable from the Green's functions of the Hamiltonian you're trying to solve. And then you regard that as a clustered DMFT solution of a very complicated correlated Hamiltonian, like the three-band Emery model. Okay, so here's the three-band Emery model. Modern calculations often use 4 coppers and 8 oxygen, so 12 atoms as the cluster. Then they embed that cluster in a medium, solve using continuous time quantum Monte Carlo for the impurity states produced by that embedding, extract the self-energy, update the Green's function, check to see if it's consistent, with the medium. If not, go around and around and around until it converges. If it converges, and the geniuses behind this theoretical mechanism have figured out how to typically make it converge. If it converges, now the medium and the Hamiltonian you started with, the one in the red box, have the same Green's functions, which are the eigenstates of the system. So if you know those Green's functions, you can calculate what's the value of the anomalous average for pair condensate. So here, I didn't say anything about electron, boson, coupling, or anything like that. I just said, solve for the Green's functions and then calculate the anomalous average. If that anomalous average, Ci up, Cj down, averaged over the whole many-body state, is not zero, then we say the theory says it's superconducting. This technique gives great power to the theorist. One thing you can check, so this is a solution from André-Marie Tremblay's group in Sherbrooke just last year, which was a big motivation for us. You know, here's our cartoon of the band structure on the left. Lower Hubbard, charge transfer, hole doped, upper Hubbard. Well, the modern DMFT solution of the three-band model has a lower Hubbard band, a charge transfer band, a hole doped band, and an upper Hubbard band with a charge transfer gap in between them. They can see the charge transfer gap directly in the solution. Okay. Now, if it's just a question of do modern theories identify the mechanism of pairing within this Hamiltonian, there's wide acceptance that the pairing is coming from what I would call charge transfer superexchange in the three-band Hubbard model. You can see, you know, world's leading theorists listed here, and now up-to-date theoretical calculations showing that this is the case in theory. The tricky part is that there has been no empirical test of the relationship between the charge transfer energy and the amplitude of the pair wave function. So none of these beautiful theories have been tested directly at atomic scale in experiment. Right. Now they give great power to the theorist. If you look at the bottom right-hand graph here, the horizontal, so now the theorist can model a material, let's say lanthanum cuprate, with the correct parameters. Then calculate how big is the pair wave function. I'm going to call the average of Ci up, Cj down, averaged over the many-body state. I'm going to call that the pair wave function from now on. So they can calculate the amplitude of the pair wave function. And now they can just, in theory, reach in and dial the value of the charge transfer energy. Okay. So for lanthanum cuprate, this was done by Weber, Howell, and Kotliar. They, you know, adjusted the charge transfer energy, and what they found out is the pair wave function amplitude changed very rapidly as you change the charge transfer energy. You're not changing temperature, you're not changing the carrier density, you're just changing the charge transfer energy, but it has a huge impact on the superconductivity. And last year, André-Marie's group did this calculation for BISCO, which is the material we can study. And they also found that the pair wave function, amplitude of the pair wave function evolves quickly as the charge transfer energy is increased. And of course, it evolves in the logical direction. As the charge transfer energy gets very, very large, the material has to turn into an insulator. And so the superconductivity has to disappear. And that's exactly what happens in the theories. All right. So here's some and now in order for us to make an experimental test, we needed to normalize the value of the amplitude of the pair wave function. So we normalized it by the value reported by the theorists for the standard materials parameters of the compound, the charge transfer energy, which actually exists in the real compound. So that allows us to look at their predictions and say, in BISCO, pair wave function amplitude, the charge transfer energy goes as minus 0.5 per electron volt. And for LSCO, it goes as minus 0.3 per electron volt. Now, unfortunately, you can't measure Ci dagger Cj. It's a complex field. You have to measure, in our universe, you have to measure a real number. So what experimentalists can measure is the magnitude squared of the pair wave function amplitude, which is the number density of the pairs. So for BISCO, the Sherbrooke prediction is that the rate of change of condensed pair density with charge transfer energy should be 0.9. per electron volt if charge transfer superexchange is the mechanism of ITC. And here we just summarized, in fact, this has been predicted for a range of materials now. So horizontal axis is charge transfer energy, vertical axis is normalized pair density, normalized by the ambient pair density that you would get for the standard parameters of each material. And that yellow cone there is the cone of interest. The astrophysicists would say, you know, the phenomena are, if charge transfer superexchange is the mechanism, then if you do the experiment, the results should lie inside that cone. All right. Now, how could you test this idea? Well, the first thing you need to do is to change the charge transfer energy. So that's a tricky one. But Gabby Kotlier and his team identified how to do that. You can do it by altering the distance of the apical oxygen atom from the copper atom. The apical atom is -2e charged. If you move it closer to the copper atom, it drives up the charge transfer energy, and farther away, it drives it down. DMFT has revealed this for a wide variety of different compounds. Roughly, you get about 1 electron volt of change of charge transfer energy for 1 angstrom of motion of the apical atom. And this concept has been around since the beginning of Cuprate research. Move the apical atom, alter the charge transfer energy. So that's the objective. So here's a cartoon now, a little movie showing the concept of our project. So on the top line here, you see the copper-oxygen plane. So oxygen is red and copper is blue when they're in the plane. And I show the apical atoms above the oxygen, the copper atoms. The line below is the actual hypothetical electronic structure in this situation. The 2p6 state is in red, and the 2 copper 3d9, 3d10 states are in blue. And below that, the amplitude of the pair wave function. Below that, the number density of electron pairs. So if we could change the apical distance, what would happen to the charge transfer energy epsilon, and what would happen to the electron pair density? Well, as a cartoon, this is what we would expect. As we move the apical away, the charge transfer energy goes down. So as we move the apical away, charge transfer goes down, but superfluid density goes up. As we move the apical towards, charge transfer energy goes up, but superfluid density goes down. That's the concept. All right, how would you do that experiment? Well, Mother Nature has been very, very kind to us. In BISCO, there is a supermodulation of the crystal in the 1-1 direction. Every 26 angstrom, 26, 27 angstroms roughly, there's a modulation there's an undulation in the position of the bismuth atoms on the surface. That's what you see on the top left-hand side. And we know from X-ray scattering, you know, exactly what's happening there. The gray dots on the top right-hand side tell us the location of the bismuth atoms in the top layer. But from X-ray scattering, we also know what's happening to the copper to apical oxygen distance inside the crystal. So when the bismuth atom is at maximum displacement along these squiggly lines here, then the copper oxygen atom in the plane is the apical to copper atom is minimal. And when the bismuth atom has minimum displacement at what we call phase pi here, then the apical distance is maximum. So everywhere in this picture, by using X-ray refinement, one could know in principle how big is the apical distance between the apical oxygen and the copper atom. And we have enough precision to know that for every atom in this field of view. Okay. Now it'll turn out the quantitative value of that number is not critical, but for the material scientists, the thing to realize is that the apical atom moves almost 0.4 angstroms. The type of pressure that you would need to do that in a controllable way is huge. So this is an amazing situation where the apical atom moves a very significant fraction of the unit cell in one of these modulations. Now, how would we visualize the energy gap between the top of the P band and the bottom of the D band? It's not that complicated. At the top of the P band, the tunneling density of states zooms up extremely quickly. And at the bottom of the empty D band, the tunneling density of states zooms up very quickly. And you can measure the energy difference between those two bands. We did it long ago when looking for the dopant atoms. And Yayu Wang has done a beautiful study of very lightly doped cuprates where he measures the same thing, the charge transfer energy. And in our study today, we're using the same technique. We just measure the energy difference between the top of the P band and the bottom of the D band. And the vertical scale in the top right-hand panel here is logarithmic. So the density of states is screaming up exponentially. Your ability to measure this epsilon is very, very good. Now, you could argue that maybe we don't measure the absolute value correctly, and possibly that's true, although the value we find is consistent with everything in the literature for multiple different techniques. But the following statement is definitely true. If there are changes in the value of the charge transfer energy, we can see those with high precision. That statement is true. Okay. And last but not least, we need to visualize the density of electron pairs. And for that, we use scanned Josephson tunneling microscopy, a superconducting sample and a superconducting tip. Under those circumstances, there's a Josephson current of electron pairs from tip to sample. The Josephson current density goes as the amplitude of the two wave function, the product of the amplitudes, and the amplitude is the square root of the number density. So in Ambergaukar-Baratov, the Josephson current through this junction multiplied by the normal resistance of that junction is proportional to the gap in the tip and the gap in the sample. And we assume that the gap in the tip, the number density in the tip, is constant. So what that means is if I square the Josephson current, if I measure the Josephson current, critical current squared, and suppose I keep the normal resistance constant, then I get a measure at that location of the density of pairs in the sample. This is the concept has been around for decades to visualize the condensed electron pairs rather than the single electron quasiparticles. However, you really can't do this as shown on the screen here. And the reason is that the junction resistance for STM is enormous. So that means the Josephson critical current is tiny. It's, few picoamps. And so that means the Josephson energy is equivalent to a temperature in the microkelvin range. You need a microkelvin STM. No one has succeeded to do this. Okay. Luckily for us, Bob Dines identified a solution when he pioneered this technique. And he showed that even if the phase is not rigid between the tip and the sample, suppose the horizontal axis here is phase difference. Suppose the phase is wandering around in some stochastic way. As long as the average of the phase over the sign of the phase is not zero, then there is an electron pair current. And the electron pair current occurs at finite voltage. But the electron pair current has a maximum Im, and the maximum is in theory proportional to the Josephson critical current squared. And the electron pair conductance has a big peak at zero bias. It's not a Majorana, don't get excited. It's a peak in the pair conductance, and the magnitude of that peak is proportional to the maximum in the pair current, which is proportional to the Josephson critical current squared. So what Dines showed is that you can measure the pair density in the sample by measuring either the maximum in the diffusive pair current or by measuring the value of the pair differential conductance at zero bias. And you have to know what the normal state junction resistance is. So either keep it constant or measure it, but then you could visualize the pairs. Okay, so to do that for Bisco, we had to make a high TC tip, which we did by exfoliating a little piece of Bisco onto the tungsten tip. After that process, we can tell that the tip is superconducting because the energy gap is 4 delta, not 2 delta in the single particle spectrum. And we can tell directly by visualizing that we still have atomic resolution. These are two completely different tips. And, this technique has been repeated in other labs as well. So it's known to work. So with such a tip, and now just using voltage differences of microvolts, this isn't the tens of millivolts you use for quasiparticle tunneling, it's just tens of microvolts. As you bring the tip in close to the surface, you see the pair current branch appearing quite beautifully. We were thrilled to see this. Now, what we want to measure is the maximum in the pair current as a function of location. So in doing that, so here's a typical topographic image of Bisco with the superconducting tip. Now, in that field of view, if we measure the maximum of the pair current at a few tens of microvolts, It looks like this at 50 millikelvin. I forgot to say, you have to be at low temperatures. It looks like that. That's one of the first, that might even be the first image ever made of an electron pair condensate in a superconductor. You're not looking at the quasiparticles, you're looking at the pairs in that image. Now that has spawned a whole new industry that I'm not going to talk about here. We were extremely lucky that in that first experiment, we found that there is a pair density wave in the cuprates. And now, you know, the Josephson tunneling microscopy is a growing field of condensed matter physics. It's an exciting field of condensed matter physics. I'm not going to talk about that, just to assure you that this technique definitely works, and several different groups now know how to use it. Okay, now let's do our experiment. We want to quantify apical distance delta, charge transfer energy epsilon, and electron pair density in BISCO. Now, in this compound, you know, we can label this 1-1 modulation by its phase. We set the phase to be 0 at the line of maximum displacement, pi at the line of minimum displacement, and 2 pi at the next maximum, and so on. So we could label the phase everywhere in this field of view. And for each phase, we know what is the apical distance from X-ray refinement. So let's do that experiment. Top left-hand side is a topographic image with a tungsten tip. We can see the supermodulation throughout the image. We can label the phase of the we can measure the phase of the supermodulation everywhere in that field of view. And from the X-ray refinement, we can estimate the apical distance everywhere in that field of view. And the apical distance is changing by more than 0.3 angstroms in that image in the left. So that's with a conventional tip. Now with a superconducting tip, we figured out how to do the same thing. We can see the supermodulation, we can measure its phase, and we can label the apical distance, you know, for the supermodulation. So that allows us to measure the phase of the supermodulation, and if you believe the X-rays, to measure the apical distance in our experiments. Now let's get to the heart of the matter. What happens to the charge transfer energy as you go along this modulation in the crystal?
Séamus,
so,
sorry to interrupt, but it's the only way to let you know that you have 5 minutes left.
Perfect. Good timing. I have only 5 minutes left to speak, so we're in good timing. So, you know, if you measure the differential conductance plus minus several volts along the red dashed line, and if I plot the differential conductance as a color scale here versus energy along that line, what you see is that the energy difference between the top of the lower band and the bottom of the upper band is modulating. And it's modulating once per supermodulation period. And it's modulating by a lot. So we were thrilled to see that. And similarly, if we have superconducting tip, we see the supermodulation of the crystal. We measure the maximum in the pair current along the red dashed line. If I plot the pair current magnitude versus energy in microvolts along that line, it's modulating. So these are facts. There's no theory involved here. I mean, you have to agree that the experiment is working, but there's no theory involved here. The energy gap between the two bands is modulating, and the Josephson current is modulating with the supermodulation. All right. So let's take that at face value. We know the phase everywhere in this field of view. We know the charge transfer energy everywhere in that field of view. So we can plot a 2D histogram of charge transfer energy versus phase and reduce that to a curve. Charge transfer energy versus phase in 17% BISCO looks like the bottom right-hand curve there, measured. You can see the charge transfer energy is changing by more than 0.3 volts. It's amazing. Similarly, you can measure the Josephson current or the Josephson conductance. We had to measure the normal state junction resistance squared and multiply, make a 2D histogram, and then show the this is the number density of pairs versus the phase of the modulation measured. And the number density of pairs is changing by almost 20%. So this is the summary of the experiment. Find the phase from the topographic image, find the charge transfer energy in red from the gap in the spectrum, find the electron pair density in blue from the Josephson current, and label them all by the phase of the supermodulation. If you do that, then you can plot number density of pairs versus apical distance, it shoots up. The bigger the apical distance, the stronger the superconductor. Haha, people predicted that 35 years ago. Charge transfer energy, it shoots down. And in fact, it shoots down on the curve, which has been expected for more than 30 years. It does exactly what's expected. All right. Now we can quantify rate of change of electron-pair condensed pair density with charge transfer energy by removing the common variable, which is phase. And here's the key result of the experiment. You can alter the condensate pair density by almost 25% in BISCO by altering the charge transfer energy by almost 35% in BISCO, by almost 30% in BISCO. This is a fact, okay? Independent of theory, this is a striking fact that you alter the strength of the superconductivity by dialing the charge transfer energy. Now, this fact, it turns out, is consistent with the theoretical predictions from the cluster DMFT calculations for hole-doped CuO2 using the Emery three-band Hamiltonian, which is an amazing fact, I have to say. We were startled, and so were the theorists. Okay, so here's the conclusion. The hypothesis is that charge transfer superexchange, charge transfer epsilon, controls the amplitude of the pair wave function. In pursuit of that, we can measure the charge transfer wave function with the charge transfer gap with atomic resolution. We can measure the amplitude of the pair wave function with atomic resolution. And they both modulate by almost 30% in BISCO because Mother Nature is kind to us. That modulation produces this relationship between pair density and charge transfer energy. Now, this is a fact in and of itself, but if you're willing to stipulate to the three-band Emery model and its DMFT solution, then the measured relationship between pair density and charge transfer energy is in excellent agreement with the theoretical predicted relationship for charge transfer superexchange being the mechanism of high temperature superconductivity. Okay, the other thing which emerges from this is that really, in my opinion, we should concentrate our attention now on powerful solutions of the three-band Hubbard model for the cuprates as a predictive theory for to find new superconductivity, to find new physical phenomena. It appears that this theory has traction on the reality of the experiments. And with that, and I'd like to acknowledge our superexchange team. Most of the work they had to do was during the pandemic. So I'm really grateful to them for their excellent work. And thank you all very much for listening.
Séamus, thanks so much for your exciting talk and okay, wonderful presentation. Are there questions? Please. Who is the first? Yeah.
Thank you. Good evening. This is Amit Karen. I don't know if you can see me. Super talk on superconductivity, very nice. But I have a question. The bottom line is that the superexchange is what counts, and the superexchange can vary with T or charge transfer gap or U, because they are not so different, U and epsilon that you had on your slide.
Hi, Amit. Yeah, thanks for that question. So
wait, I didn't ask yet.
we don't study superexchange J. We have no access to it. We just study the charge transfer gap.
I know, but I just want to say that in the literature,
and it's an empirical fact that the charge transfer gap controls the superconductivity. So discussions about J don't play any role in that empirical fact.
In any case, can I finish my question? In the literature, there are papers in the past that show connection between TC and J by Reeks and Raman and USR. And so my question is, can you pinpoint what is exactly new, or what was not in those papers that you are reporting?
Very good. TC is not a measure of the amplitude of the pair wave function in a correlated superconductor. That's known very well from the three-band Hubbard model. So TC is not a proxy for the condensate.
All right.
More questions? there is like, okay, no more questions from the audience, Séamus, can I ask just simple-minded question concerning the experiment? So,
Yep.
okay, am I understand correctly that what you definitely see in the experiment, that you have something what you could call, let's say, self-induced or developed for one or another reason, electronic granularity, and then the transport which you see. And okay, in a superconductor is sort of like hopping between these, let's say, inhomogeneities in a condensate density. Is that
Right.
and that's
Yeah.
why and that's
Yeah,
why
let me share screen and answer that question. So obviously, for many decades, there's been the hypothesis that the condensate of electron pairs in the cuprates is heterogeneous. But when we visualize it directly, it's not. The heterogeneity you see here is due to zinc atoms, which were substituted on the copper site in order to test the technique. And in fact, away from the zinc atoms, the superconductor, the condensate itself, is highly homogeneous. So this came as a big surprise to us, and we're still trying to understand what it means. And even though the single electronic structure is heterogeneous, the condensate appears to be homogeneous. But this is now at the frontier of our capability to do scan Josephson. So it remains, it's a mystery that remains to be solved.
Thank you. Well, if there are no more questions, let's thank Séamus once again for a wonderful presentation.